Right, guys, welcome. Yesterday we were looking at the calculations that involving the equilibrium of esterification, whereby we are looking at carboxylic acids reacting with alcohols to form esters. But today we're going to look at those equilibria that involve hydrogen, iodine, and hydrogen iodide. So let's take an example of the question given. They're saying that 3 moles of hydrogen and 1 mole of iodine were heated together in a sealed tube. So our constant should be 3 moles of hydrogen, 1 mole of iodine were heated together in a sealed tube at 500 degrees until equilibrium was established. They want us to calculate the number of moles of hydrogen iodide present in the equilibrium mixture at 500. Given is the Kc, which is 50. Okay, so now here what we need to do for part A, we need to first write the equation. So the equation for the reaction will be hydrogen. Hydrogen is a gas. It is reacting with the iodine, which is also a gas. They establish equilibrium forming hydrogen iodide, which is also a gas. So we need to write the initial moles. For this case, the initial moles of hydrogen are 3. We said 3 moles were mixed with 1 mole and heated. So we have 3 moles here. We have 1 mole heated. Then in this case, initially, we do not have any moles of hydrogen iodide. After getting those initial moles, we need the moles that reacted. Moles which were reacted or formed. We assume if the moles reacted for hydrogen were X, because of the mole ratio 1 to 1, this one will be X. But for the case of hydrogen, it will be 2X. Reason, the mole ratio is 1 to 1 to 2. So after having gotten those moles, now we get moles at equilibrium. Moles at equilibrium, write the whole word. To get moles at equilibrium, for this case, we shall be getting the initial moles minus the moles that reacted. Initial moles minus moles that reacted. But for this case, if you get 0 minus 2x, you get negative 2x. But moles can't be negative, so it will keep 2x. Then if we assume that the volume of the vessel was 1 liter, then these moles are the same as the concentration. So concentration, since you're not given any volume, so the concentration will be 3 minus x also, 1 minus x, 2x. Why did I do that? I took the volume, taking volume of the vessel as 1 decimeter cubed. Now, for this case, I'm going to write the expression for Kc, and I'll have Kc. Kc is going to be equal to the concentration of hydrogen iodide, because we say the product of the molar concentration of the product is raised to the appropriate power. So it is hydrogen iodide, but because of 2 here, it will be raised to the power 2 over the concentration of hydrogen times the concentration of iodine. We can now substitute. So our Kc is 50, is given as 50. 50 is equal to concentration of hydrogen iodide, it is 2x, then squared out of concentration of hydrogen, 3 minus x, then 1 minus x, like that. So we solve that equation for the value of x. So in this case, means we have 50 is equals to 4x squared over 3, I'm expanding the bracket, minus 3x minus x, which is minus 4x, then plus x squared. Cross multiply, we shall be having 150 minus 200x, then plus 50x squared is equals to 4x squared. So this is the same as you bring a 4x squared this side, so it will be it will be 46x squared minus 200x, and of course plus 150 is 0. So our x will be equal to, we substitute in the quadratic formula, so it will be minus b, which is 200 plus or minus the square root b squared, be negative 200 squared minus 4 times s, 4s, so it is 4 times 46 times 150 out of 2a, which will be 2 times 46. So this one will give you the values of x. Now, after putting in the quadratic formula, you can now put on your calculator and get us the answer. You may not go through all those steps of solving. So our x will be equaling to, we have 3.384, and our other value of x will be equal to 0.964. But remember, the value of x cannot exceed the initial moles which we have. So if in case you have like initial moles at 3, and you find you have the value of x as a 3.384, it means that we shall discard this and take this, because even moreover here, if you substitute for 3.384, you'll be getting negative moles, which is not possible. So we shall say discard 3.384. Reason why has it been discarded? It gives a negative value for moles of hydrogen. Okay. It gives negative value for moles of hydrogen and iodine at equilibrium. For moles of hydrogen and iodine at equilibrium. So if that is the case, then it means that our value of x is therefore equal to 0.964. But the question is, calculate the number of moles of hydrogen iodide present in the equilibrium mixture. So at equilibrium, the moles of hydrogen iodide is 2x. So if x is 0.964, it means that the moles of hydrogen iodide, we shall just multiply. So moles of hydrogen iodide at equilibrium will be equaling to 2x, which are going to be equal to 2 times 0.964, all right, which is going to be equal to 1.938 moles. And that is it. Part B, they want us to explain how the concentration of iodine at equilibrium can be obtained. If you understood the experiment that we used to determine the Kc for the reaction between hydrogen and iodine to form hydrogen iodide, there is a point where we break the tube under potassium iodide, okay, to dissolve the iodine. Then that iodine is titrated against standard solution of sodium thiosulfate, since the concentration of the sodium thiosulfate is known, we can get the number of moles of sodium thiosulfate, and then we use the mole ratio to get the moles of iodine. As simple as that. So for the case of part B, I'm going to write and say the tube is broken. The tube is broken under aqueous solution of potassium iodide okay, to dissolve the iodine present dissolve the iodine present to dissolve the iodine present at equilibrium. So after doing so, we titrate the resultant mixture. Resultant mixture is titrated with a standard solution of sodium thiosulfate The resultant mixture is titrated with a standard solution of sodium thiosulfate using starch, indicator. Now, after doing that, the amount of iodine present is calculated using the equation we shall have iodine plus thiosulfate ions we form iodide ions and tetrathionate ions. Okay. So that is it that we can take. Then let me do some other question here. Let me do some other question here. Question 2. Okay. Our question 2 is saying moles of hydrogen and 18 moles of iodine, 18 moles of iodine were heated in a 1 liter sealed tube at 465 degrees Celsius. When equilibrium was attained, the tube was cooled and found to contain and found to contain 30.8 moles of hydrogen iodide. Part 1, give a reason why the tube here I forgot rapidly. Give a reason why the tube was rapidly cooled. 2, calculate the value of equilibrium constant Kc for the reaction taking place in the tube and the degree of dissociation of hydrogen iodide. So for this case, if you look at Roman 1, we have been talking about this in the experiments. They say why the tube is rapidly cooled. We simply rapidly cool the tube to stop the reaction. Stop the reaction, that is the first point to make. Stop the reaction and fix equilibrium. There's another point, and fix equilibrium such that equilibrium does not adjust itself, does not adjust itself to the equilibrium value at a lower temperature, to the equilibrium value at a lower temperature. Yeah, that point we've been looking at it in experiments, so I may not delay on it. Part 2, they want us to calculate the value of Kc for the reaction taking place in the tube and the degree of dissociation of hydrogen iodide. Interesting. So here, write the equation first. We have hydrogen. Hydrogen is a gas, plus iodine. Iodine is a gas. We are forming hydrogen iodide, which is a gas. So initial moles, hydrogen 25, hydrogen 18, but initially we don't have hydrogen iodide. So moles that reacted or formed if this is X, mole ratio X, then 2X here. So then we can get equilibrium moles. Moles at equilibrium, we just subtract 25 minus X, 18 minus X, and this one will keep 2X. So if we take the, before that, the question they say that after equilibrium being attained, the tube was rapidly cooled and found it contained 30.8 moles of hydrogen iodide, meaning at equilibrium, this tube contained 30.8 moles of hydrogen iodide. Now, we need to get the value of X first by using this information. If at equilibrium it contained 30.8 moles of hydrogen iodide, and here you have the moles at equilibrium as 2X, it would imply that 2X is equal to 30.8 because all these are moles at equilibrium. All right. So for 2X is equals to 30.8, we can get our value of X by dividing by 2, and it is going to be 15.4. After getting the value of X as 15.4, we can get moles of hydrogen at equilibrium, moles of iodine, and moles of hydrogen iodide. So, remember that since even we were told that it is 1 liter vessel, then it means that the concentrations are the same because we divide by volume, which is 1 liter, 1 liter. So, concentration of hydrogen will be equaling to 25 minus the value of X, which is 15.4. And this is giving us 9.6. Concentration of iodine, it is 18 minus 15.4, which is 2.6. Then the concentration of hydrogen iodide, since at equilibrium it is already given, it will keep 30.8. Then now we get Kc. So Kc is equal to the concentration of hydrogen iodide squared divided by concentration of hydrogen raised to the power 1 times concentration of iodine raised to the power 1. So it will be equal to hydrogen iodide, which is 30.8 squared over hydrogen, this is 9.6 times 2.6. So we shall get the value of Kc as 38. The units it has no units because this is moles per liter squared, moles square per meter squared, per liter squared, then the same because you multiplied two of them. So we shall take the value of Kc as that. Then now they are saying that also calculate the degree of dissociation of hydrogen iodide. Degree of dissociation of hydrogen iodide. Now, for the case of degree of dissociation, of hydrogen iodide, it means that now you have hydrogen iodide dissociating. It is dissociating to give hydrogen and iodine. So initial moles if I rate it to be C, this one will have nothing and this one will have nothing because now it is this one dissociating. So the reactant we have this. Then from here, we can get moles dissociated or formed. Since we are looking at dissociation, if this is C alpha, because we have to bring in the degree of dissociation. So it is C alpha, then this one will be C alpha out of 2, right? C alpha out of 2, and even this one will be C alpha out of 2. Because if this was 2 moles, and this is 1, 1, so it would be a half because of the mole ratio. Then from there, we get moles at equilibrium. Moles at equilibrium will be, we shall get C minus C alpha, even here. This is C minus C alpha, but this one will keep C alpha over 2, and even this one we shall keep C alpha over 2. Now, from there, we can get concentration at equilibrium. We shall divide by volume, so it will be, say C 1 minus alpha over volume, and this is C alpha over 2 volumes, C alpha over 2 volumes. Now looking at this, our value of Kc is going to be equal to concentration of hydrogen ion of hydrogen raised to the power 1 times concentration of iodine, because we begin with the products. Then we divide by a concentration of hydrogen iodide, then everything is squared. So it would mean that our Kc will be equal to, we substitute, it will be C alpha over 2 V, everything squared because they are the same. Then we divide by hydrogen iodide, which will be C into 1 minus alpha over V squared. So from what we derived in experiment, we come up with alpha squared over 4 1 minus alpha, everything squared as our Kc. But I want you to note that the Kc for the dissociation of hydrogen iodide or anything, for the Kc for the dissociation is the reciprocal of the Kc when the substances are reacting. So in other words, Kc for dissociation of Kc for dissociation of hydrogen iodide will be equal to the reciprocal of Kc for reaction between hydrogen and iodine. Hydrogen and iodine. What does it mean? Implying that the Kc for dissociation of hydrogen iodide will be equaling to 1/38. So now I substitute that into this. So it would mean that 1/38 is equal to alpha squared over 4 into 1 minus alpha, everything squared. Now I'm going to solve for the value of alpha. So yeah, this is 38. Alpha squared is equal to, this is, if you square this first, then you multiply 4, it is going to be 1 minus 2 alpha plus alpha squared. So it is going to be 4 minus 8 alpha plus 4 alpha squared. So you bring everything this side, we shall have 38, shall have 34 alpha squared, right, plus 8 alpha minus 4 is equal to 0. Put in Bordo's formula. So our alpha will be equaling to negative b, which will be minus 8, plus or minus the square root of b squared will be 8 squared minus 4 times a, which is 34, times c, which is negative 4, over 2a, which will be 2 times 34. So our value of alpha is either negative 0.48. I told you after substituting, you can go and put the formula in the calculator and solve. Your calculator may not have alpha. Just put the way you put other equations, then you take those values you get as values of alpha, or 0.24. But alpha cannot be negative, so we discard or we eliminate alpha is equals to negative 0.48, and we take the value of alpha as 0.24. That way, you will have managed the question. Very interesting. Very interesting. So that is our example number 2. Then example number 3. When stoichiometric amounts of hydrogen and iodine were allowed to reach equilibrium, in a 1 liter vessel at 450 degrees Celsius and 1.01 exponent 5 Newton per meter squared, that is pressure, 1.56 moles of hydrogen iodide were formed at equilibrium. Calculate the equilibrium constant Kp. Now we need Kp. So when they say stoichiometric amounts, to show that, it means that we have to write a balanced equation to show the stoichiometry of the reaction between hydrogen and iodine. So we have hydrogen gas plus iodine gas form hydrogen iodide. So here we shall have the initial moles here we have 1, as you can see, 1 stoichiometric amounts, which means that the amounts were shown by the equation. So 1 mole, then 0 initially. Then moles that reacted, or moles that were formed, for hydrogen, if it is X, iodine will be X, and this will be 2X. Then moles at equilibrium, we shall have 1 minus X, 1 minus X, and 2X. Now, they are saying that when the stoichiometric amounts of hydrogen and iodine were allowed to reach equilibrium in 1 liter vessel, meaning the concentration will divide by volume, which is 1, 1, 1. So at 450 and 1.0 Newton meter square, 1.56 moles of hydrogen iodide were formed. So if 1.56 moles were formed, then it means that those are the very moles of hydrogen iodide, 1.56, they are moles at equilibrium. So I will equate this one and this. Okay, so it would mean that 2x is equal to 1.56. Therefore, our x will be 0. After dividing by 2, 0.78. Right? So after getting this, we can get total moles at equilibrium. Since we're given pressure, we need total moles at equilibrium. So total moles at equilibrium will be equaling to 1 minus x plus 1 minus x plus 2x. And that is equal to 2. Because this 2x, this minus 2x, they cancel, so you have 2. Now, after getting moles at equilibrium, let's get pressure of hydrogen. Pressure of hydrogen would be moles of hydrogen, which is 1 minus x, that is 0.78, over total moles, that is 2, then times the pressure, total partial pressure, 1.01 times 10 to the power 5. So you will get the moles of hydrogen as 1 times 10 to the power 4 Newton per meter squared. Then we also get pressure of iodine. Pressure of iodine is the same because it is 1 minus, you get moles of iodine, divide by total moles, multiply by total pressure. Don't say that they are the same and you don't show the working. So it is 1.111 exponent 4 newtons per meter, newtons per meter squared. Newtons per meter squared. Then we also get pressure So also get pressure of hydrogen iodide would be equaling to 1.56 moles at equilibrium over total moles, then times 1.01 exponent 5. So this one gives us 7.878 exponent 4 newtons per meter squared. So they want the value of Kp. So Kp, you know that Kp is the same as partial pressure of hydrogen iodide squared. You begin with the products. You need to remember how we write Kp values over partial pressure of hydrogen times partial pressure of iodine. That is how we write it. But the only logic behind here is that when you're given pressures, you need or you must look for the total moles at equilibrium, because to get partial pressure of a particular substance, we get moles over total moles times the total pressure. That is the only logic behind that. So this is going to be 7.878 exponent 4 squared over 1.111 times 10 to the power 4 squared, because they are the same. So solving that, you get the value of Kp as 50.28, and you call it a question. You call it question. Let's have this done also. The more examples, the better you understand. So, question 4, 1 gram of hydrogen and 127 grams of iodine are allowed to attain equilibrium in an evacuated container of volume 10 decimeters cubed at a temperature of 450 degrees Celsius. If the equilibrium constant at the same temperature Kc is 50 degrees Celsius, calculate the Roman 1 value of Kp, Roman 2 total pressure in the container, and Roman 3 partial pressure of hydrogen in the container. Okay, so we are given masses of hydrogen and iodine. So we need to first get moles, all right? We need to first get moles. So we really know that to get moles, we need molar masses. So molar mass of hydrogen is equals to 1 times 2, which is equals to 2. And molar mass of iodine is, there are 2 atoms, so we multiply by the atomic mass, 127, which is 254 grams. So after getting the moles, of course, we can get the for the case of we've gotten molar masses of hydrogen and iodine, right? So let me get moles of hydrogen. Moles of hydrogen will be equaling to mass over molecular mass, which is 0.5. Moles of iodine will be equaling to 127 over the molar mass, 254. It will give you 0.5 still moles. After getting these moles, then we can get moles of hydrogen iodide. Moles of hydrogen iodide from the ratio, from the equation, we know that hydrogen 1 mole plus 1 mole of hydrogen, they give 1 mole of hydrogen plus 1 mole of iodine, they give 2 moles of hydrogen iodide. So it will be 0.5 times 2, which will give 1 mole. So and remember, Kc is equals to 50. Now, since they need Kp, we looked at the relationship, the expression for the relationship between Kc and Kp in our first lesson. So I want to remind you that to get the value or to get the answer, we need to also be knowing the molar gas constant, which is 8.314 joules per mole per Kelvin. Then we need to also be knowing volume. Since volume they gave us 10 decimeters cubed, we need to put it in meters. So it's going to be 10 exponent -3 meters cubed, right? Then temperature, they give us 450. So if temperature is 450, temperature is 450 degrees Celsius, we have to convert it to kelvins. So it's going to be 450 plus 273. We put it in kelvins, and it is going to be 723 kelvins. All right. Then now, of course, in that same formula of the relationship, we have delta N, whereby delta N refers to the number of moles of the reactants minus, rather, of the product minus the total moles of the reactants. So it will be 1 minus 0.5 plus 0.5. This will give you a 0. So it is 1 minus 1, which is 0. Then now, then it means that Kp from Kp is equal to Kc okay? RT power delta N. Our Kp is going to be equal to, if you fit the value of Kc, RT, that is 8.314 times 723, then delta N, which is a 0. So the whole of this, n number to the power 0 is 1 times 50, it gives 50. So the value of Kp is 50. Interesting. So don't assume that it is equal and you don't work it out, because by luck, we have found it equal, but it does not guarantee that it must be equal. Okay. Then on from here, they need us to get the total pressure in the container. Total pressure in the container. How do we get total pressure in the container? We have to write the equation and proceed from there. So part 2, we have hydrogen plus iodine to give us hydrogen iodide. Well, so here, initial moles, we have initial moles. Hydrogen was, we have already calculated the initial moles there. So there was 0.5, 0.5, but initially you don't have hydrogen iodide. Then you also look at moles reacted or moles formed. If I let this one to be x and x, here we should have 2x. Then moles at equilibrium. Shall have 0.5 minus x, 0.5 minus x, then 2x. Now, when we are to talk about pressures, we need to look for the total number of moles. So total moles at equilibrium will be equal to 0. Let me call it n, 0.5 minus x plus 0.5 minus x plus 2x. We shall get total moles as 1. Remember, our PV is equals to any RT. So if PV is equals to any RT, our P is going to be equal to N, which is 1, times R, 8.314, times T, which we had converted into 723 kelvins, over volume, we shall divide by volume, which is 10 times 10 to the power -3. So this one will give you total pressure as 610.11022 newtons per meter squared. That is how we get the total pressure. Then the last part wants the partial pressure of hydrogen. So if you have to get the partial pressure of hydrogen, it means that we get moles of hydrogen, okay, over total moles times the total partial pressure. So to get moles of hydrogen, of course, we need to first get the value of x. And how do we get the value of x? Since we can easily use Kc, you know that Kc is equal to hydrogen iodide, which the power 2 over concentration of hydrogen times concentration of iodine. So if we substitute, it will be 50 is equal to concentration of hydrogen iodide 2x squared at equilibrium over 0.5 minus x times 0.5 minus x. So when you work on this, so it will be 50 into 0.5 minus x, 0.5 minus x is equals to 4x squared. So this equation will reduce to 92 x squared minus 100x plus 25, giving 0. So the value of x is minus b, so it will be 100 plus or minus the square root of b squared, which is negative 100 squared, minus 4 times a, which is 92, then times c, which is 25. Then everything is divided by 2a, which will be 2 times 92. Okay, now solving this equation will give us the value of x as 0.390 or 0.697, but moles shouldn't exceed the initial moles, so we cannot take 0.6, and therefore we shall discard x, which is 0.697, because it gives negative values of 0.5 minus x. So if we discard that, it means that our value of x is 0.390. Now, if we need the partial pressure of hydrogen, partial pressure of hydrogen is equal to number of moles of hydrogen, which is 0.5 minus x over the total moles at equilibrium, 1 times the total partial pressure, which is 60,11022. So this is the same as 0.5 minus 0.390 over 1, of course, to keep that, then times 60,11022. So working out to this will give us the partial pressure of hydrogen as 66,1212.442 newtons per meter squared. I'm going to do you the last question. Then after that, I get you work to do. The degree of dissociation of 0.5 moles of hydrogen iodide was found to be 5% at a certain temperature in 1.5 decimeters cubed vessel. Capture the equilibrium constant Kp. So for this case, if you have to calculate the value of Kp, that's right, the equation. It is the degree of dissociation of hydrogen iodide. So we have hydrogen iodide dissociating to give hydrogen and iodine. Initial moles 0.5 here, 0, 0 initially. Then moles dissociated or formed. It should be 0.5 times the value of degree of dissociation. Then these ones will be 0.5 alpha over 2, 0.5 alpha over 2. Then now there we get moles at equilibrium. It will be 0.5 minus 0.5 alpha. Then this will be 0.5 alpha over 2, 0.5 alpha over 2. Now, they told us that the degree of dissociation was found to be 25%, meaning that alpha is equals to 25%, which is equals to 25 over 100. That gives 0.25. So that is the degree of dissociation. The moment they talk of Kp or anything to do with pressure, we need to first get the total number of moles at equilibrium. Total moles at equilibrium will be equal to 0.5 minus 0.5 alpha, 0.5 alpha over 2, 0.5 alpha over 2. Yeah, adding 0.5 alpha over 2 plus 0.5 alpha over 2. The whole thing is going to reduce to 0.5. So the total moles at equilibrium is 0.5, meaning that if we need a partial pressure of hydrogen, it will be equal to partial pressure of hydrogen will be 0.5 alpha over 2 times total pressure. Actually, it is the moles of hydrogen divided by the total moles, right? Then multiply the pressure. So moles of hydrogen, if you evaluate this, because you have the value of alpha already, so it is going to be 0.3 moles of hydrogen will be we have 0.5 alpha over 2 for hydrogen. So if we multiply by alpha 0.5, then we divide by 2, we shall have 0.0625, right? We divide by the total moles at equilibrium, which is 0.5. Then we shall multiply by the partial pressure. Right. Still, the partial pressure of hydrogen iodide is going to be equal to, for hydrogen iodide, we have 0.5 minus 0.5 alpha. We substitute for alpha here and work on it. It is going to give you 0.375 over the total pressure, no, total moles, 0.5. Then we multiply by the total pressure. All right. So, let's see. For this case, this is it. This is hydrogen. To get hydrogen, I got 0.5 times the value of alpha, which is 0.25. Divided by 2, then times the total pressure. All right, so of course you can get the moles at equilibrium Okay, you can get moles at equilibrium for all these. You can get moles at equilibrium, moles at equilibrium, moles at equilibrium. Then you divide by the total moles multiplied by the pressure. Okay, so I skipped that step, but you can show it. Yeah, you can write moles of hydrogen iodide at equilibrium, evaluate. Moles of hydrogen at equilibrium, evaluate. Moles of iodine at equilibrium, evaluate. Then get the total pressure. Now, interestingly, after getting all these, I assume that my total pressure was P, right? So I came up with this. And now, also the pressure of iodine, partial pressure of iodine will be still, because it's the same as hydrogen, so it is 0.0625 out of total moles, 0.5, everything times the partial pressure. So after getting all that, we can get the value of Kp. Value of Kp is the same as 0. Of course, you can first write the expression, is the pressure of hydrogen times pressure of iodine over the partial pressure of hydrogen iodide, but everything squared. So substitute pressure of hydrogen and iodine, they are the same, so 0.0625 over 0.5 times partial pressure, but we are squaring since they are the same, then divided by, for the case of hydrogen iodide, 0.375 over 0.5, then times P, everything squared. So I'm completing it from there. So it is going to give you, the numerator will reduce to 0.015625 P squared out of 0.5625 P squared. So these P's can cancel, and we shall have a value of Kp as 0.0275. As simple as that. Very many questions can be done in this particular case. Very many questions can be done. It's a matter of revising the work. So I'm leaving you with two numbers to do. That's also supposed to be question 6. You are going to do it. It is 3.20 grams of hydrogen iodide were heated at 450 degrees Celsius in a glass bulb, of volume 800 cubic centimeters. All right. When equilibrium was attained, when equilibrium was attained, the bulb was rapidly cooled at room temperature and then broken and then broken under a solution of potassium iodide, right? The iodine formed required 36.0 cubic centimeters of 0.2 molar sodium thiosulfate solution in presence of starch indicator. In presence of starch indicator for complete reaction. Number 1, explain why the bulb was broken under potassium iodide solution. 2, calculate the equilibrium constant Kc for the reaction at 450 degrees Celsius. I'm going to give you a hint, but I will not do it. I'm just going to give you a hint. Yeah, this one we looked at the reason as to why the bulb is broken under potassium iodide, simply to dissolve iodine. Okay, to dissolve iodine present, because that iodine, the reason is to dissolve iodine present at equilibrium, because iodine will react with iodide ions from potassium iodide and we form triiodide complex. So we break it under potassium iodide solution in order to dissolve the iodine present at equilibrium. Then if they want you to calculate the equilibrium constant here, for this case, you're having mass of hydrogen iodide. First get the moles of iodide, of hydrogen iodide. Actually, in brackets, hydrogen is 1 and iodine is 127. Hydrogen is 1, iodine is 127. Now, for this case, we can get moles of iodine also, because you need to ask yourself why we introduced sodium thiosulfate. There is question 2, example question 2, where we looked at where they were asking us to briefly describe how the amount of iodine would be determined. To determine the iodine, we have to titrate against sodium thiosulfate in presence of starch indicator, meaning that since sodium thiosulfate is known, we can get moles of iodine by writing the reaction equation between iodine and thiosulfate to give tetrathionate ions and iodide ions. So that way, if these moles are in 1,000, we get moles in 36, then we get, from the mole ratio, we get the amount of iodine, or we get the moles of iodine. That way we can push it. Now, okay, if they say that if we can get moles of iodine here, those are the moles present at equilibrium, then the equation from the interpretation, you'll have the moles of iodine at equilibrium as per the procedure, then equate them to these moles which you get from this equation so that you get the value of alpha. But I want you to push and see if your value of Kc will be equaling to 0.04. Another thing that you need to mind about here, they have said that the volume is 800 cubic centimeters. So if the volume is 800 cubic centimeters, it means that to get the concentrations, we shall be getting moles, we multiply by 1,000 over 800 cubic centimeters, because that volume must be converted to a liter. Okay, so to convert to a liter, the moles you'll be getting will be the moles in 800. So you'll be saying maybe to get the concentration of hydrogen iodide. Okay, you can get the moles which you will get times 1,000 divided by this volume. Then you get your value of Kc. The value of Kc has to come out as that. Then I feel like giving you another question here. Yeah. Give you another question. The equilibrium constant for the dissociation of hydrogen iodide is 0.02. 1 mole of hydrogen and a third moles of iodine are heated together at 450 degrees Celsius. Calculate the mass of hydrogen iodide present, at equilibrium. Should get the mass as 82.176. Hint: the equilibrium constant for dissociation, okay, is 0.02. But they have given us moles of hydrogen and moles of iodine, meaning that if the Kc for the dissociation is this, what about the Kc for association of hydrogen and iodine? It would be the reciprocal of this still. So that is what you need to know. Kc will be equaling to 1 over Kc for the dissociation. So this one will give us the Kc. Then now you proceed with other workings, because you have to have that. Since they didn't give us the moles of hydrogen iodide and we're given moles of iodine and hydrogen, it means that these are the two associating to give us the other. So the answer should come up as this. That is the hint I can give. So till next time, wish you the best, guys.